Welcome to the DX Today podcast, your daily deep dive into the AI ecosystem. I'm Chris, and joining me as always is Laura.
Hey, Chris. Great to be here on this Friday in late May. We've got a story today that genuinely made me sit up and rethink what reasoning models are actually capable of doing.
Lay it on me. The headlines this week have been all about IPO rumors and Google's developer conference fallout, so it'll be refreshing to talk about something with a bit more depth and weirdness.
So earlier this week, on May 20th of 2026, OpenAI quietly dropped a research note saying one of their general-purpose reasoning models had cracked an 80-year-old open problem in pure mathematics.
When you say cracked, I assume you mean cracked in the rigorous, write a real proof, hand it to a Fields medalist, get a thumbs up sort of way, not just guess the answer.
Exactly that. The model produced a constructive proof that refuted a long-standing conjecture connected to the famous Erdős unit distance problem, which Paul Erdős first posed all the way back in 1946.
For listeners who haven't spent their evenings staring at combinatorial geometry textbooks, can you give me the elevator pitch on what the Erdős unit distance problem actually asks in plain language?
Sure. Imagine you scatter some number of dots on a flat piece of paper, say n dots, and then you count how many pairs of those dots happen to be exactly 1 unit apart.
Right, so you're not measuring total distance or anything fancy. You're just counting the pairs that land on a perfect unit separation. That sounds almost trivially simple as far as math questions go.
It does sound innocent, but the question becomes deceptively hard when you ask how large that count can possibly get. The answer depends on where you place the dots, and the optimization is brutal.
So Erdős' whole career was basically asking questions that sound easy at a cocktail party and then turn out to require 30 years of mathematics from 4 different subfields to even partially answer.
That's a perfect summary of the man. He posed thousands of problems like this, and he famously attached cash prizes to many of them, partly to motivate students and partly because he had a sense of humor.
How much was the bounty on this specific problem, just out of curiosity? Because I always love the idea of a mathematician walking around with index cards listing problems and their dollar values.
For the matching upper bound on the unit distance count, Erdős had offered $500, which by the standards of pure mathematics is actually a respectable bounty for a single open conjecture.
$500 for 80 years of frustration sounds like a bargain. So what did mathematicians believe was the optimal configuration of points before this OpenAI result came along and rewrote the picture?
For decades, the consensus, going back to Erdős himself, was that you basically couldn't do meaningfully better than arranging your dots in a square grid. Like graph paper, a perfect square root of n by square root of n lattice.
That feels intuitive to me. Square grids feel maximally efficient. They tile the plane perfectly. Every point has exactly 4 immediate neighbors at distance 1, and it's hard to imagine doing better than that.
And the count from a square grid grows in a very specific way. Roughly n times the logarithm of n to a small power, which gave a clean upper bound conjecture that lasted generations of researchers.
Okay, so set the stage for me. The conventional wisdom for 80 years was that square grids are essentially optimal, and Erdős believed there was some matching upper bound, proving they couldn't be beaten by much.
Right, and dozens of brilliant combinatorial geometers chipped away at this for decades, finding small improvements, but nobody seriously believed the underlying square grid intuition was actually wrong at the deep structural level.
Until this week. So what did the OpenAI model actually find? Did it discover some clever rearrangement of the dots, like a hexagonal grid or some exotic fractal pattern that everyone had somehow missed?
This is where it gets weird and genuinely beautiful. The model didn't reach for geometric tricks at all. It connected the problem to algebraic number theory, which is a completely different branch of mathematics altogether.
Algebraic number theory? That's the world of prime factorizations and exotic number systems and Galois groups and things that, on the surface, have absolutely nothing to do with dots on a piece of paper.
Exactly, and that's what makes this so striking. The model built point configurations using algebraic number fields, specifically leveraging a structure called infinite class field towers and a result called the Golod-Shafarevich theorem.
Pause there because you just casually name-dropped 2 pieces of machinery that most working mathematicians have not personally used in years. Class field towers are not exactly undergraduate material, even at strong universities.
They really aren't. Class field towers come from a deep corner of number theory dealing with how prime ideals factor as you climb infinite chains of field extensions, and they're notoriously slippery objects to handle.
And the Golod-Shafarevich theorem, if I remember my graduate algebra correctly, is a result about infinite class field towers existing under certain conditions on the ramification of primes in the base field.
That's the one. And that theorem is precisely what allowed the model to actually construct, not just postulate, an infinite family of point configurations in the plane that beat the square grid bound by a polynomial factor.
So the construction isn't just one counterexample. It's an infinite parameterized family that beats the conjectured optimum by a polynomial factor as n grows, which is a much stronger and structurally meaningful result.
That's the part that's blowing mathematicians' minds. A single counterexample can sometimes be a lucky accident, but an infinite family with a polynomial improvement means there's a real structural phenomenon being uncovered here.
And the size of that polynomial improvement actually matters too, because in combinatorial geometry, the difference between log factors and polynomial factors is often the difference between a curiosity and a paradigm shift.
Right, a polynomial gap means the asymptotic growth rate of the maximum unit distance count is genuinely faster than anyone believed, which forces every textbook chapter on this corner of discrete geometry to be rewritten by
Who has actually looked at this proof? Because in pure math, a claimed proof and a verified proof are very different things. And AI-generated math has a checkered history of looking right and being subtly wrong.
Fair point. The proof has been informally examined by an absolute murderer's row of leading mathematicians, including Timothy Gowers, who is a Fields medalist, along with Noga Alon, Anant Shankar, and Jacob Zimmerman.
That is a heavy hitter lineup. Gowers in particular is famously careful and skeptical, so the fact that he's at least informally endorsing the construction is a meaningful signal that something real is happening here.
Right, though we should be clear about one thing. Formal journal peer review is still pending, and pure math peer review can take many months or even years for results this technically involved across multiple subfields.
Good caveat. So zooming out for a second, what makes this announcement structurally different from earlier AI math results, like DeepMind's Alpha Proof, or the various lean-based theorem-proving systems we've covered on the show before?
This is the key distinction that I think is underappreciated in the news coverage so far. Previous AI math systems were highly scaffolded, problem-specific, or designed to translate proofs into formal verifiers like lean.
Right, Alpha Proof, for instance, was trained specifically on Olympiad-style problems and used a tight feedback loop with the lean proof assistant, which is impressive but also very narrow in what it can attack.
Exactly. And Alpha Geometry similarly used a specialized geometry engine paired with a language model. They're brilliant pieces of engineering, but they're built tightly around the structure of the problems they're meant to solve.
Whereas in this case, OpenAI is claiming a general-purpose reasoning model, not a math-specialized system, just attacked an open problem from the working mathematician literature and produced a novel, non-trivial construction unprompted.
That's exactly the framing OpenAI is leaning into. And if it holds up under formal peer review, it suggests we may finally be approaching what people have called the autonomous research assistant threshold for science.
Although, devil's advocate for a second, we don't actually know what the model was prompted with, how many attempts it made, or whether it had access to retrieval over the relevant number theory literature beforehand.
That's a totally fair pushback. OpenAI has not yet published the exact prompts, the number of sampled attempts, or the chain of reasoning that led to the construction, which makes fully independent replication much harder right now.
And without those details, it's hard to know whether this represents a genuine leap in reasoning capability or whether it's closer to a very lucky search through a well-chosen space of mathematical objects and proofs.
True, though even the lucky search interpretation would still be significant. The space of possible algebraic number theoretic constructions is astronomically large, and stumbling onto the right one is itself a kind of meaningful discovery.
Fair. So let's talk about implications. If general-purpose reasoning models can occasionally crack open problems in pure mathematics, what does that mean for adjacent fields like theoretical physics, computer science, material science, or chemistry?
I think the honest answer is we don't fully know yet, but the upside scenarios are genuinely thrilling. Open problems in lattice-based cryptography, in protein folding edge cases, in quantum error correction codes, and beyond.
Lattice cryptography is an especially interesting one to flag, because the entire post-quantum security stack that NIST has been standardizing rests on the assumed hardness of problems closely related to these geometric constructions.
Exactly. And if AI reasoning models start finding novel lattice constructions or unexpected algebraic structures, that could either strengthen those schemes by revealing weaknesses early or destabilize them in ways that nobody is prepared for yet.
All of those are areas where the search space is enormous, the underlying math is brutal, and a single clever construction can unlock entire downstream industries or solve problems that have stalled the field for decades.
Right, and the pattern we're seeing is that reasoning models seem to be especially strong at making unexpected analogies between distant fields. Exactly the kind of move that produced the algebraic number theory connection here.
That cross-domain analogy capability has always been one of the harder things to pin down in AI evaluations, because it doesn't fit neatly into benchmark categories like math, code, reading comprehension, or factual recall.
Exactly. And that's why this kind of result, fuzzy as it currently is in terms of replication detail, matters more than another point of improvement on a closed benchmark like MLU or GPQA or any other static test.
So what should listeners take away from this story? Is this a watershed moment, or is it one impressive data point that we'll need to see replicated and stress tested over the next 6 to 12 months?
I'd say it's both, honestly. It's the first credible claim of an autonomous AI math discovery on a long-standing open problem, but the field still needs independent reproduction, full peer review, and many more examples.
That feels right. We've seen too many AI math headlines that didn't survive close scrutiny, but the validators on this one are serious, and the technique they describe is structurally novel, not a known proof recycled.
And in the wider context of this week's AI news, with OpenAI reportedly filing a confidential IPO and Anthropic posting its first projected profitable quarter, this kind of scientific result is actually the more durable story.
Right, and the business headlines move markets in the short run, but a reasoning model that can contribute novel mathematics to the literature changes what these companies are actually for on a much longer civilizational timescale.
Exactly, and that's why I wanted to spend a full episode here rather than fold it into a news roundup. The Erdős result, if it survives review, will be remembered long after this quarter's IPO chatter fades.
Well said. Listeners, we'll be watching closely for the formal peer review verdict and for any follow-up papers from OpenAI or independent groups attempting to replicate or extend the construction in the coming weeks and months. That's all for today's episode of the DX Today podcast. Thanks for listening, and we'll see you next time.